Okay, mechanical work. Let's define mechanical work, and we'll put it to use. Keep in mind the derivation that we did from Newton's second law in kinematics, right? So form one was that all forces cause change in kinetic energy. Now I want to just say something really carefully, and we're going to say this. Ultimately, all interactions, all changes come from interaction. So even jiggling energy, effectively behind that, there's some interaction, some force. Now, you're not going to be able to keep track of it, which is why energy is so great, because you don't have to keep track of all the forces. We can keep track of something called energy, which is not a thing. It's not like money or pens, right? But we can keep track of it. So just keep in mind that we built this house here that reflects our understanding that came from Newton's laws. So we got this idea, work from all forces, whether you can make them simple or even on the atomic level from jiggling and so on, causes a change in bulk kinetic energy. We often call it mechanical work energy formula. Mechanical work being bulk motion, movement of things, not worrying so much about my jiggling atoms or radiation. Energy, it is the energy added or taken by a force. So when we're doing energy accounting, we can have positive work, meaning some energy is going into the object and maybe speeding it up, maybe lifting it, we'll get into that and things like that. Okay. Or you can take it away, you can slow it down. And usually there are multiple forces. As you know, F net equals ma. Okay? So you've got to deal, each force can do work. But it's the net or total work that will give you the change in kinetic energy. And again, we'll throw in potential energy in a moment too. Okay, so it could be positive or negative, and that just means whether the force is trying to speed it up. Gravity, on the way up, slows this object down. So it's trying to slow it down. Force of gravity is down, but I can make it speed up. Still, gravity is trying to slow it down. All right, so anyway, plus or minus, we'll get into that. A force is an interaction. Ultimately, all changes come via interactions, from interactions. Keep that in mind. So this is a clever little bookkeeping device. The conceptual intuition is not hard. We've said it many, many times. Force parallel to velocity increases the speed and hence the kinetic energy. Notice the vector notation. Put arrows on top of vectors. Don't on top of scalars. I draw vectors like this, where that shows me the direction and that tells me the amount. Some people do it like that. That's okay. We've shown with tension that you can get into trouble with that notation, so whatever it is. Force opposite the motion or the velocity decreases speed, or will try to. If there's other forces, it might not win, but it's trying to decrease the speed and trying to decrease the kinetic energy. Force perpendicular to velocity doesn't change the speed or kinetic energy. It does no work. So it's there. It can change your direction, remember, but it doesn't. Energy is a scalar, so it doesn't care if you change direction. It's doing something. It takes something to turn something, right? It takes a force. And you might say, well, I'm tired. I keep trying to turn you. Okay, you're using up some energy, but it's not going to that object. So we're going to see. What we're interested in is how much you're transferring by interaction. I could push all day. Oh, man, I've been working all day. What have you been doing? Well, I've been moving this wall. Well, no, you haven't. But I'm really tired. I've been pushing all day. I've been exerting a force all day. Yeah, fine, but you haven't got anything done, so we're not paying you. And you're fired. Okay, so what we're talking about is what goes to that object, not what you did. Those issues are issues of efficiency, which we'll get into. And that can be tricky. Okay, cool. So in general, the component of force parallel to the velocity increases speed and kinetic energy. Parallel or opposite the velocity, parallel to negative velocity, decreases. And perpendicular does no work. Now, here's an important thing. Velocity is always tangent to the path, whichever way you're going at that moment. Okay? So it requires forces to speed it up, slow it down, turn it. Tangent to the path. So let's go over here. It's the component of the force parallel to the path, with or against, that does positive or negative work. And you can just see it. If you draw your picture, you can see it, and then we can calculate it. The component perpendicular to the path doesn't do any work. It's there, it's doing what it's doing, it's turning you, but turning doesn't change a scalar, right? Okay. Mathematical definition of work then. We need to see and draw the path and the force to apply this. And again, there's lots of ways you can do the puzzle. You can look at one force at a time. There could be lots of forces. You could look at the total force or the net force, right? Vector. So we've got vectors, but we're going to end up with a scalar. What product do we use? The scalar or dot product. Okay. Now this definition we often don't use. We use kind of simpler cases. But this is the basic definition of the energy added or taken away via a force. Really important idea for now, and especially for later work in engineering and physics courses. An integral is not a state function. You can't have an integral at a moment. You can't evaluate the area under curve at a point. There's no area. So it's between two states, and again, I like to use earlier to later states. It's not what we call a state variable. Force can be at any moment. Velocity can be at any moment. Kinetic energy can be at any moment. The way we've defined potential energy, we'll see later, can be at any moment, and this distinction is going to be important. But work, so it doesn't make any sense to write something that books used to write, and people have gotten rid of that. Delta work doesn't make any sense, because that would be work later minus work earlier, and if you understand that that doesn't make sense, then you understand what I'm saying, is that work inherently is something that happens from an earlier time to a later time. Okay, cool. So what is it? How do we use it? Well, first off, let's look at the units. What are the units? Yeah. It's a Newton times a meter, or any other unit you want, but still it's going to be force unit times this path unit, so that's going to be called a joule, as you know. And we explored how much a joule is. Go back to the how much videos. It's important to have an intuition for how much a joule is. Not too much. It's the graphical area, so sometimes we'll say graphs, and the area can be positive or negative, because it's not physical area, it's graphical area, between, say, the fx curve and the x-axis. So over here I got an fx curve and an x-axis. If you've got an equation for fx, fine, you can integrate it. If you just have some geometric shape like rectangles and triangles, you just treat it like a rectangle on a triangle, but if it's below the axis, we say that's negative. Okay, fine. And you can get that through various data collection methods too. It's a good little example. Any kind of integral, as you know, can be looked at, the slope, the graphical area, and so on. So common simple cases are these. When the force is parallel to the path and it has a constant F or F strength, then, for example, the path doesn't have to be constant. As long as the force is constant and you're pushing parallel here, well, then what is the angle? The angle between the force and the path, well, the path there is parallel, so the angle is 0. At any rate, in this case, we're going to see that the force does a work in this case, from that force, is the force times the displacement along the path. Or so if you want, you can say the distance along the path. Is it positive or negative? Well, you can tell. You're trying to speed it up. Maybe there's friction not letting you speed it up. It doesn't matter whether the thing's speeding up or not. You're contributing positive energy. And then that's nice and easy. You don't have to do an integral. You don't have to do anything. It's just the force times however far you went along the path. Fine. Now, if you're going the opposite direction, what's the answer? Of course, if you're doing this now, this picture is unclear. And I drew it purposely unclear. In fact, this one is too. So inherently I'm thinking here, if this force is parallel to the path, then I'm going to start here maybe at state 1, state 2, state 3, state 4, state 5, state 6, and I'm going with the motion. So notating the states is helpful. I mean, I could be going to the left. That'd be fine. I've drawn it here, so this is state 1, state 2, state 3, state 4, state 5. So that tells me that I'm traveling over here to the right, and along here my force is opposite my path. And in that case, the work due to that force is going to be opposite or negative. It's going to try to slow it down. It's the strength of the force. And then it's simply the distance along the path. If it's horizontal, that's easy. If it's on an incline, that's kind of easy too, because it's just the distance along that flat path. But this works for curved paths too. Okay. All right. Cool. Everybody good with that? You guys cool with that? It's either trying to trying to add energy, that is, trying to speed it up, or trying to increase kinetic energy. If there's other forces, it might not win, or it's trying to take it away. Okay, so you can look one by one. Now, of course, over here, in general, if the force is constant and there's an angle between the force and the path that's constant, so let's look at a couple of cases. Suppose this guy moves over this way. Then it's only the part of F that's going with the motion that does work. So which part of that force does work? I like to draw components dashed, right? How much is that?
Cosine, F cosine, theta.
F cos theta. Now I don't care if that's in the negative direction. If I call that plus X, oh, that's in the negative direction. I don't care. That's a really tricky little thing because you get so used to doing that. It doesn't matter. The question is, are you trying to add energy at least? Or are you trying to take away energy? Are you trying to speed it up? Or are you trying to slow it down? Now, there's also the F sine theta. Does that do any work? Because it's perpendicular. It could turn it, but that doesn't change kinetic energy. So, does no work. So it's only this part. So in this case, the work due to that force would be positive or negative. Positive. Times the force times the distance along the path. In this case, it might be delta x. But notice, I threw this little curveball here on purpose. If I call x positive this way, you might say, oh, look, delta x is negative 2 meters. If I throw that in there, I'm going to get a negative, and all of a sudden I'm saying, hey, that force is taking energy away. No, that's wrong. You know that the force is trying to speed it up. So you got to be careful. You have to think just that old conceptual way and get this right. Okay, so here, strictly might be a way of saying times that, or the distance along the path. Distance is positive. Displacement might not be, right? So I could also write that as the distance along the path. Hopefully everybody's cool with that. If I flip the coordinates, say that, it doesn't matter. And yet we often write the vectors in terms of coordinates. I'm going to show you that on the next video. All that matters is that force trying to add energy or take energy out. Okay, cool. So that's a pretty nice equation there. It's only the part of force parallel to the path. And that's why we use the scalar, also called dot product, of the two vectors in our integral form. But this is how we often use it, and it could be plus or it could be minus. Now, if it moves the other way, so if I've got a situation where the thing moves the other way, and yet, in this case along a horizontal surface, and yet my force is still like that, then I realize, and you can do this two ways, here's my force, I'm keeping it constant, so it's nice. The angle between these two is theta. Draw that like this. And so you could do it this way. You could write this. You could say, hey, the work due to that force is by definition, right? So you have the definition, and then you've got your old work energy theorem. So, you know, those are your tools. Explore them. You might, if you know the change in potential, the change in kinetic energy, then you know what the total net work is. But if I look at them one by one, it's this. I could say it's F cos theta times the distance along the path. And in this case, theta is greater than 90 degrees, so cos theta is negative, right? And so inherent or implicit there is that negative sign. You could also use this angle, I'm just going to call it alpha, and then I could also say that that is equal to F cos alpha times that distance, and then I'd have to put in the negative sign, because F cos alpha would be this way, F cos alpha, and clearly that's opposing the motion, trying to slow it down. Whether or not it does, you have to look at all interactions for that. Okay, so how do we do it?
You're good. Another 5 minutes.
So the last little bit to set us up for the next time, and I'll repeat this, is that a lot of times the cases are pretty simple. Just if you look at the force and you look at the path, you can see whether the force is trying to add energy, increase speed, increase kinetic energy, however you want to say it, or decrease, or if only one component is doing the work, or if it's perpendicular to the path, then it's not doing any work. It's there. Now, before I go on that one, be really careful, because the normal force, people often want to say the normal force does zero work. And, well, what direction is the normal? This is it. Go through a checklist. What direction is the force? What direction is the motion? What's the angle between them? 90 degrees. How much work? None. The normal force is not doing work. And as you slide along a surface, the normal is perpendicular to the surface, so the normal force doesn't do any work. That's true. But watch this. The normal force is doing positive or negative work. Now the normal force is doing... The normal force is which direction? The motion is, both are up. So the force is with the motion. Normal force is trying to speed it up. Now the normal force is still up, and the motion is down. So the work from the normal force is negative, because it's trying to slow. In fact, it is slowing it down, because if you didn't have the normal force, it's going to do that, right? Okay, that's cool. So, wait a minute. Get rid of this guy. The normal force is doing positive or negative work? Positive. How do you get that? Look at the force. Don't jump to the answer. That's the biggest mistake people make, is just jump to the answer. Just go through the steps. The force is up, the motion is up, the work is positive. The force is up, the motion is down, the work is negative. The force is up, the motion is perpendicular, the work is zero. You go along a surface, still the normal is perpendicular to the surface, and so if you go along the surface, the work is zero. However, if the surface is moving, that's when it's kind of tricky, like, oh, wait a minute, I got to be careful. Now, gravity, the force of gravity, what direction is it? Down. So as I go up, the work due to gravity is force, motion, opposite. Work due to gravity is negative. Now the work due to gravity is still down. Now the motion's down, so the work due to gravity is positive. Why? Because on the way down, it'll increase the kinetic energy. On the way up, it'll decrease, decrease, increase. Normal force is doing positive, gravity is doing negative, and the kinetic energy is constant. Delta K is. Normal force is doing negative, gravity is doing positive, kinetic energy you see is constant. So it really does go, well, wait a minute, let me get away from the math and think about this, right? So you can treat the force of gravity in this way on the left side of the equation with interactions, or as you know, in Form 2 of our work energy theorem, you can move it over and do something really cool. That's what we're going to be doing next. And to prep you for that, we're going to say, hey, what is ds? Well, you can move however you want to. And ds is just a little piece of that. So that means you could move some in the x direction, some in the y direction, and some in the z direction. You can also write that in so you can move in or out radially and not around. You can put in polar coordinates. There's an interesting thing about these guys. So you're moving this much in that direction. The unit vector, so-called, really should be called the direction vector, can be written, that's the same as this. So just realize it is something. It's not just, it's something. It doesn't matter which order you write it. So we might touch on that a little bit. We'll see. It's pretty nice. And in general, though, we can write it like this. So we're going to do that. And of course, in general, any force can be written in terms of its components. And this was where the mathematical formalism, Fy, Fz, k hat, can be really nice because too much is going on to keep track of. And yet our equations are math. We crank that wheel, we set it up correctly, we have some intuition from really simple problems, and then we crank that wheel and we can do things like fluid mechanics and vector calculus for fluid mechanics, aerospace engineering, all kinds of cool stuff. And the setup is where your intuition is, and then when you get a result, you think about, hey, did that make sense? Did I crank the mathematical wheel correctly, etc. So let's go into the invention of the concept of stored or potential energy from a conservative force.